All right, so we are going to start a new chapter today, or a new unit per se. We are going to be covering special right triangles and trigonometry. A lot of people wanted this lesson or this unit, so I'm going to make sure that you get it. We're going to start with 9.1, which is the Pythagorean Theorem. I'm not going to spend too much time on this because I know you all know the Pythagorean Theorem and how it works. So this part's going to go by really quickly, and then we're going to learn the other two lessons during this video. So we've got our Pythagorean Theorem. Okay, it basically says if I have a right triangle, I can take the two legs, A and B. I can take leg 1 of A, square it, add it to B squared, which is leg 2, and it should equal the hypotenuse squared, which is C. A squared plus B squared equals C squared. We all know this. We've talked about Pythagorean triples before. Okay, 3, 4, 5 is the most common one, 5, 12, 13, 8, 15, 17, 7, 24, 25, and there's a bunch of them. Okay, they're all here if you want to look at them for reference. Now, if I want to find the value of x in this problem, I'm looking, x is on the hypotenuse, which is C. So I'm going to do a squared plus b squared equals c squared. So I'm going to do 5 squared plus 12 squared to get whatever x squared is. Once I do all that math, 5 squared is 25, 12 squared is 144. So x squared equals 169. So x equals 13 when I get the square root of both sides, okay? Again, because this is a video, you can pause if you need to. If you want to work on a problem before I get through it, pause it, work on it, and then check your answer with me. The converse of the Pythagorean theorem. Even though you may not have learned this way, I know that if you did take 7-8, you should have learned this as well, okay? It's basically saying if I have a triangle that's not labeled, so in this case I've got this triangle ABC. I don't know if it's a right triangle or not because there's nothing here that tells me that this angle is a right angle, okay? So what I can do to try to prove whether or not this is a right angle is take the two smaller sides, which are the legs, square each one, add them together, and see if it gives me the length of the longest side squared. So again, I'm going to do a squared plus b squared equals c squared. If both sides are equivalent to each other, if I take a squared plus b squared, and that is in fact equal to whatever c squared is, then this triangle has to be a right triangle, okay? So tell whether each triangle is a right triangle. You can pause the video if you want to go over these yourself. I'm only going to do A. B is the same exact thing. If I'm looking at this, I've got 7, 8, and root 113. If you're not sure which one the longest side is, okay, because this has a root over it, well, think about a perfect square that you know that's close to 113. Well, there's 100, and the square root of 100 is 10, which is greater than 8 and 7. So the square root of 113, which is greater than 100, should be greater than 10, which is greater than 7 and 8. So I'm going to do 7 squared plus 8 squared equals the square root of 113 squared, which is just 113. And when I do that math, it looks like this. Yes, the answer to B is here as well if you want to go over that. 7 squared is 49, 8 squared is 64. Add them together, you get 113. And since 113 equals 113, A is a right triangle. If you did B and you went over it, you're going to see that both sides are not going to be equivalent to each other. In fact, they're off by 1, which means that they're definitely not equal. So B is not a right triangle. Okay? B is not a right triangle. The Pythagorean Inequalities Theorem. This is basically saying if I have if I have a triangle, okay, doesn't have to be a right triangle. Why does it not have to be a right triangle? Because this is going to tell you whether the triangle is acute or obtuse or right. We already know that if we do a squared plus b squared and it equals c squared, we have a right triangle. Well, the Pythagorean Inequalities Theorem says, if I take a squared plus b squared and that sum is greater than whatever the longest side squared is, or c squared, then the triangle has to be acute. If I do a squared plus b squared and that sum is greater than c squared, then the triangle is obtuse, meaning this angle is greater than 90, this angle is less than 90, okay? Remember, acute means that the triangle has three angles that are less than 90. And if it is obtuse, one of the angles, which is opposite of the longest side, is greater than 90 degrees. This is the only really new theorem that we're covering in this lesson. So let's put it together. First off, verify that segments with lengths of 4.3 feet, 5.2 feet, and 6.1 feet form a triangle. Then, if it is a triangle, is the triangle acute, right, or obtuse? Well, the first thing you need to do is use the triangle inequality theorem, which we learned, I believe, in Unit 6, okay? That basically tells us if I add up, and we also learned in 7-8, if I add up the two smaller sides, that sum has to be greater than the largest side. Actually, if I take any of the two sides and add them up, that sum has to be greater than the third side. So we're gonna test that out. And if we do test that out, we find that it checks off for each one, okay? I can do each inequality, add up the smaller sides, greater than the biggest side. 9.5 is greater than 6.1. 4.3 plus 6.1, that sum's gonna be greater than 10.4. And then same thing here, that sum is greater than 4.3. Now, these two are kind of unnecessary because you're adding 4.3 to 6.1. 6.1 is already greater than 5.2. Same thing here, 6.1 is already greater than 4.3. So there's no real point in doing this. This is what you really needed to look for. And since they are, or these sides do make a triangle, now I have to check, is the triangle acute, right, or obtuse? So I'm gonna take the two smaller sides of 4.3 and 5.2, square each one, add them together, and see if that's equal to, greater than, or less than 6.1 squared. So if I do that, here I've got 6.1 squared. I don't know what goes here because I don't know if it's equal, less than, or greater than 4.3 squared plus 5.2 squared. If I square these two, I get 18.49 plus 27.04. And then on the other side, I've got 37 and 21 hundredths. And 37 and 21 hundredths is indeed less than 45 and 53 hundredths. So this has to be an acute triangle, okay? Because c squared is less than a squared plus b squared. And that's it for this lesson. Again, most of this was review, so if you fast forwarded until this point, great. Completely understandable. Let's move on to 9.2. Special right triangles, okay? So we're gonna be dealing with special right triangles. There are two special right triangles. The first one is a 45, 45, 90 right triangle, okay? This is an isosceles triangle, meaning that two of the sides are equal to each other. Guess which sides are equal to each other? The ones that are directly across from the 45-degree angles. If these two angles are the same, notice how they're both 45, then the sides that are across from them, or their corresponding sides, also have to be equal to each other, okay? Now, anytime you have a 45, 45, 90 triangle, the reason why this is a special right triangle is because these two sides are always going to be the same regardless, And the hypotenuse is going to be whatever that side is times root 2. Or if you really want to write that down without all the sentences, hypotenuse equals one of the legs times root 2. Pause the video to write this down. Please make sure you know this. Now, the next slide, it says finding side lengths in 45, 45, 90 triangles. We want to find the value of x. Notice that x is the hypotenuse. I know it's the hypotenuse because it's directly across from the 90-degree angle. And then we want to write our answer in simplest form. We're going to keep them in terms of roots. Okay? Now, according to the 45, 45, 90 theorem, if this leg is 8, then this leg has to be 8 because both of these have to be 45. And the hypotenuse has to be one of the legs, which we said was 8, times root 2. So x is equal to 8 root 2. Now b follows the same pattern. We've got a leg, and then we know that this is the hypotenuse because it's directly across from the 90-degree angle. And since the hypotenuse is equal to a leg times root 2, we just divide the hypotenuse by root 2. And that leaves us with 5. So x equals 5. If you want to see the work, it's right here. Again, we know the leg is 8, and hypotenuse is equal to leg times root 2. So x equals 8 times root 2, which is just 8 root 2. Down here, same situation. This time we have the hypotenuse, we don't have the leg. If to get 5 root 2, we did leg times root 2, then we can set 5 root 2 equal to x root 2, divide both sides by root 2. The root 2's all cancel, we're left with 5 equals x. So the value of these legs is 5. Now the second type of special right triangle is a 30, 60, 90 right triangle. Okay? Now, what I want you to understand is, and we've kind of talked about this, but again, it was a couple years ago. Notice that inside of the triangle, if I'm looking at the angles, the smallest angle is 30. The smallest angle is always going to be directly across from the smallest side. So see where it says x? This is the smallest side. It's directly across from the smallest angle, which is 30. The next smallest, or the next biggest, however you want to look at it, angle is 60. Okay, this is in the middle because it's 30, 60, 90, 90 being the biggest. 60 degrees is in the middle, meaning that the side across from it or its corresponding side is the middle or medium-sized side. Okay, and then 90 is always going to be across from the hypotenuse, which we know is always the longest side. Now the pattern for any 30, 60, 90 triangle is going to be that the shortest leg is always x, the longest leg is always x times root 3, and the hypotenuse is always twice the smallest leg, so 2x, okay? It's always gonna follow this pattern. Now, when I tell you that a 45, 45, 90 and a 30, 60, 90 follow these patterns, that doesn't mean that it's always gonna be so evident that you're always gonna have something like x, x root 3, and 2x, okay? It's not always gonna look explicitly like this. It is always gonna follow the pattern of x, x root 3, and 2x, but you might not always have a root here. Maybe the smaller leg has a root, okay? And this one's gonna be a number that's times root 3. That's fine. And this number is always gonna be double whatever the smaller leg is. So let's look at an example. Finding side lengths in a 30, 60, 90 triangle. This says find the values of x and y. Write your answer in simplest form. So if I'm looking at this, I see I've got 9. 9 is my medium-sized leg, and I know that because, or my longest leg, because it's across from the 60-degree angle. Okay. Notice exactly what I said. This side is technically x times root 3, but there's no root 3 attached. Well, then that means that this side has to have some sort of root 3 attached to it. But to get this 9, I had to multiply whatever this was by root 3 to get 9. So I have to figure out what that was. Okay, so how do I set this up? Well, the first thing I need to do is, if I know that the longer leg is equal to the shorter leg times root 3, I need to set that up. Well, the longer leg is 9, the shorter leg is x, we don't know what that is yet, and it's times root 3 to get 9. So how did we get that? We're going to divide both sides by root 3. So 9 divided by root 3 equals x. Now, if it were anything but a root, I would tell you could leave your answer this way. But since there is a root in the denominator, and we are not allowed to have roots in the denominator, we need to fix this, right? We need to simplify this so that we have no roots in the denominator. So what we're going to do to get rid of this root 3, or this root in the denominator, is multiply the numerator and denominator by root 3 over root 3. The reason we do this is because this is equivalent to 1. It does not change the value of this fraction, but it also eliminates the roots from the denominator, because root 3 times root 3 is root 9, and the square root of 9 is 3. So now my denominator goes from being root 3 to 3. And what happens instead when I multiply by root 3 over root 3, I end up with 9 root 3 over 3, which we can actually simplify to 3 root 3. So the value of x is 3 root 3. Now, if I had 3 root 3 as x and I wanted to get this value, let's say this was z, I would multiply 3 root 3 times root 3, which would give me 9. Okay? So this is still root 3 times larger than the smaller side. Now, if we want to find y, we're going to do something a little bit different. We know that the hypotenuse, which is where y is, and I know it's the hypotenuse because it's across from 90-degree angle, the hypotenuse is twice the length of the shortest side, which was x. So all we need to do is take 3 root 3, which we found out was the value of x, and double it. And if I do that, I end up with 6 root 3, because 3 root 3 times 2, or doubled, is 6 root 3. So the value of y ends up being 6 root 3. This is why I gave you guys that disclaimer that when we are looking at these theorems, same for the 45, 45, 90 as well, that it's not going to look exactly like this. I'm not just going to have a whole number as my smallest side, and then that number times root 3 as my largest leg, okay? And then it's not just going to be 2 times a number, it's going to be it could be 2 times a number with a root attached to it. And this might be just a whole number, because when I multiply root 3 times root 3, they cancel each other out. At least they cancel the roots out. And you're left with a whole number here, just like we were in this example, where we had 9, okay? And that's the end of 9.2. Let's talk about 9.3. This one can get a little fuzzy, so please pay attention. Okay, we're going to talk about similar right triangles. And we're going to start off with the right triangle similarity theorem. What this is saying is, if I have a right triangle, so pretend that this line isn't here for a second. Okay, CD. Pretend CD is not here for a second. If I just had a triangle ABCD, okay, if I have a right triangle ABCD, and I decide that I need or want to bring down an altitude And remember, an altitude is just a segment that comes from a vertex that creates a 90-degree angle or is perpendicular to the opposite side, okay? Notice how CD is perpendicular to AB or AD or BD, okay? And now what happens? Well, when I bring down this altitude, I now have 3 triangles. I have the original ABCD, which was this large triangle. And then when I bring down CD, it also splits it up into 2 smaller triangles, ACD and BCD, okay? Being the smallest triangle. Now the right triangle similarity theorem says if I bring down that altitude, I now have 3 right triangles. Every single one of these 3 right triangles is similar to each other. ABC, ACD, and BCD are all similar to each other, okay? They're all similar to each other. Okay. So in this example, it says identify the similar triangles in the diagram. I know when I named the triangles earlier, I did not name them in the correct order that I was supposed to in terms of the letters. You need to make sure that every single corresponding vertex is in the correct order, okay? So when it says identify the similar triangles in the diagram, I know that there's 3. There's this large one. I'm gonna start at R and call this R. This is the smallest vertex. It's opposite the smallest leg. So R, bring it down to T, to S, okay? Notice that RTS is what I'm calling the triangle. It's going from the top vertex to the right angle, to the next vertex, back up the hypotenuse, okay? If I'm going to go with this triangle here and say that it's similar to RTS, I need to call this RUT. Yes, I understand that spells rut. So R, which is the smallest vertex, down to U, which is where the right triangle is, to T, and then back up the hypotenuse. Same thing with the smallest triangle, okay? T is my smallest vertex. U is where the right angle is. I know it's a right angle because the other side is right angle, which means this angle has to be a right angle. From U to S, so TUS. Okay, that is the order that these would go in for me. Now, if you started with T, you might have had different order. If you started with U, you might have had a different order. Okay. In the solution, they decided to go with TSU, so they went from the smallest vertex to the hypotenuse to the right angle. If you did that, you'd go RTU because you're going from the smallest vertex to the hypotenuse to the right angle. And then from R, which is the smallest vertex, to S, down the hypotenuse to S, and then to the right angle, and then back up the longest leg. Okay. Core concept, the geometric mean. Now, don't worry too much about understanding what this is doing by itself, okay? Just know that when you are solving a geometric mean, you're taking 2 positive numbers, you're gonna multiply them together, and they're gonna be equivalent to another positive number squared, okay? This comes from a proportion of A over X is equal to X over B. Where is this coming from? Well, we're about to see an example, okay? We're about to see an example in a couple slides. Let's talk about finding a geometric mean. So if A and B represent two positive numbers, all I have to do is multiply them together and get the square root of them to find out what the geometric mean is. So if I'm given, find the geometric mean of 24 and 48. What this is telling me to do is multiply 24 and 48, get the square root of it, and you're going to get the geometric mean. Now, if I do that, this is what happens. I get x squared equals AB, just like we were told in the previous slide. X squared equals A is 24, B is 48. Now, if I want to solve for x, I need to get the square root of both sides. So x equals the square root of 24 times 48. You're more than welcome to multiply them together. However, because 48 can be broken down into 24 and 2, what they decided to do here was to take the square root of 24 times 24, which is 24 squared. And since there's two of them, we can just take the 24 and put it on the outside and then keep the root 2 underneath. Okay, so the geometric mean is 24 root 2. I don't expect you to do this. I would prefer that you stay with 24 root 2. That is a more exact answer, and that is the correct answer. Okay, so the geometric mean of 24 and 48 is 24 root 2. Now, why in the world did we learn the geometric mean? Well, we found the geometric mean because when we have three similar triangles, we actually have a way of finding different parts of it by using geometric mean theorems. The first one being the geometric mean altitude theorem. This says that if I have a right triangle, like I have like this, ABC, and there's an altitude, notice CD is my altitude, that divides the hypotenuse of the triangle into two separate segments. Notice that my segments are AD and BD, okay? There's two segments now. They're split at this point of intersection with CD. If I want to know the length of this altitude, okay, which actually gives me either the shorter leg of ADC or the longer leg of CDB, notice that this altitude is a leg of both of these two triangles, right? We took the big triangle and we split it up into these two triangles. They both share CD. It's the long leg of the small triangle, and it's the short leg of the medium-sized triangle, okay? If we want to know how long CD is, we find the geometric mean of both of these segments. So we take whatever AD is, and we multiply it by whatever BD is, and set it equal to CD squared. So that's the geometric mean altitude theorem. The leg theorem, the geometric mean leg theorem, is very similar. Again, we have a big right triangle, ABC. We have an altitude coming down and splitting the hypotenuse into two segments. Now, if I want to know what the length of each leg of the right triangle is, okay, when I say each leg of the right triangle, I mean this leg of the big right triangle is BC, and AC is the other leg of the biggest right triangle, ABC, okay? If I want to find these two legs, then what I'm going to do is I am going to take this hypotenuse. Notice how it's broken down into segments, AD and DB, but the whole hypotenuse is AB. Depending on which leg I want to find, let's say I want to find CB first, okay? Notice how this segment BD is adjacent to the leg I'm trying to search for, okay, that I'm trying to find the value of, CB. Because BD is adjacent to it, I can take BD and multiply it by the entire hypotenuse meaning I'm finding the geometric mean between this small segment and the whole hypotenuse in order to find CB squared. Okay, so I'm going to take BD, multiply it by the whole hypotenuse, AB, and that should be equivalent to CB squared. Now, if I want to find AC, I'm still going to find the geometric mean between the adjacent side and the whole hypotenuse. Okay, so that means I'm going to take AD because AD is adjacent to AC, or CA, however you want to look at it. And I'm going to multiply AD by AB, which is the whole hypotenuse, to get the geometric mean, and that should be equal to AC squared. Okay? And again, we're doing this to find these lengths. In the top one, we found the geometric mean between the two segments, the two smaller segments that the hypotenuse was broken up into, to find the altitude. That's the only thing that I'm going to find if I multiply AD times DB. It's going to give me the altitude. Okay, the geometric mean between AD and DB is going to give me the altitude. In the bottom, if I take the adjacent side of one of these two legs and I multiply it by the whole hypotenuse, then I'm finding the geometric mean of one of these two legs. It just depends on whether I'm looking for AC or CB. If I'm looking for AC, then I multiply the hypotenuse times AD because AD is adjacent to AC. If I want to find BC or CB, then I have to multiply this smaller segment, which is adjacent to CB, of BD, and multiply BD by the entire hypotenuse, AB. Okay, and it's going to give me the shorter leg of the whole big triangle. I know that was a lot, so let's try putting this into practice. Don't let this confuse you with the wording. Really just understand what's happening with these formulas first. Once you figure out these formulas, the words are going to make more sense. Okay? Break down the math to get the English. Usually I understand it's kind of vice versa, but in this case, break down the math to get the English. So here we're going to use the geometric mean. We want to find the value of each variable. So in A, we've got big triangle. We've got the hypotenuse broken down into segments, 6 and 3. And we know that the altitude is what we're looking for. It's x. Since we're looking for the altitude, we need to use the first theorem, the first geometric mean theorem, which basically says I have to take 6, which is this segment up until the altitude, and then the other segment of 3 and multiply them together, then get the square root. Well, 6 times 3 is 18, and the square root of 18 is what we're looking for. That's going to be equivalent to x. The square root of 18 can be broken down into root 9 and root 2, so 3 root 2 would be my answer for x, and I'm going to show you that in just a second. Now, notice how I want to find the smaller leg of the large triangle. The altitude breaks up the hypotenuse into 2 and another segment of 5, meaning that the whole thing, the whole hypotenuse is 7. So if I want to find this small leg, first thing I need to identify is, besides the hypotenuse, is what is my adjacent segment? Well, the adjacent segment of the hypotenuse is 2. So now I'm going to find the geometric mean between 2 and the hypotenuse, which is 7. So 2 times 7 equals y squared. And if I do that, y equals the square root of 14. So again, for the first one, we did 6 times 3. We got 18. We got the square root of both sides. Root 18 can be broken down into root 9 and root 2. Root 9 is 3, so we're left with 3 root 2. In the second one, our adjacent side was 2, not 5. Our adjacent side was 2. The whole hypotenuse was 7, because 2 plus 5 is 7. Multiply those together, you get 14. Y squared equals 14. Get the root of both sides, and you get y equals the square root of 14. We cannot break down root 14 into anything that has a perfect root. They're all technically prime roots, so we're just going to leave them alone and keep it as root 14. If this went by a little bit quick, again, you have the option of rewinding, rewatching, breaking things down, trying them yourself, which is what I really recommend that you do. And then you can start your class/homework depending on how much time you have right now, which is this. All right. Let me know if you have any questions. You can email me. I know I wasn't here. I apologize for that. Have a great day and enjoy.